Hi everyone, my name is Sven Wang and I'm a postdoc in Youssef Marzouk's group, and I'll be presenting today on some work that we did in the past year, which regards measured transport methods for density estimation. So what is the broad goal that we're concerned with here? In formal terms, what we're trying to do is to learn a complicated probability distribution pi. We might only have access to pi via some samples. And so yeah, doing this is a central goal in statistics and machine learning and rare event modeling. To be a bit more specific, I could aim for two things when I talk about learning a probability distribution pi. The first thing would be to estimate pi by some estimator pi hat. And the second goal will be to generate new samples that are distributed approximately according to pi. So an example of this would be, for instance, if pi is a distribution of real-world images and I see a lot of instances of real-world images, and then I want to estimate the distribution of those and also come up with a sampler that generates new pictures which look like they occurred in real life. Here's a schematic image of how many modern generative modeling strategies work. So these include, for instance, variational autoencoders, generative adversarial networks, normalizing flows, and more recently, score-based generative models, which are based on diffusions. Very roughly speaking, what happens in all of those is that I have some simple probability distribution, for instance, a unit Gaussian, and then this learning algorithm learns some kind of transformation, often parameterized by a neural network, that transforms this unit Gaussian into a more complicated distribution, which is the generated distribution, and the generated distribution is supposed to resemble the true data distribution, which I've observed through samples. And so a lot of these methods, in fact, have as an underlying principle that they are somehow learning a transport map. So the transport map then pushes a simple distribution into a complicated distribution, right? Especially normalizing flows and VAEs can be interpreted this way. Applications include, for instance, images, as I mentioned, text, videos, and also learning rare event distributions. Okay. So a transport map S, once you have such a transport map, you always induce a coupling between a reference and a target. So specifically, S will push pi into eta. And okay, so these transport methods, they fix some typically very simple and tractable eta. So for instance, that could be unit Gaussian, like in the previous image. It could also be taken to be the uniform distribution if one is on a bounded domain. And then you find from your data an invertible map S that couples your target pi and eta. So it pushes pi into eta. And once you found such an invertible S, both of those goals of learning probability distributions that I mentioned, namely estimating the density and generating samples, are simultaneously addressed. The density estimation problem is addressed simply by a plugin. So once you have estimated S, a resulting estimator for pi is simply by pulling back the reference density under this estimated map. And the sample generation problem is solved because it's very easy and cheap typically to generate samples from the reference. So if you can generate sample Z from the reference eta, then you simply have to plug those random samples into the deterministic transport map S inverse, and you'll arrive at approximate samples for pi. Right, so the whole challenge is to learn the transport map. Okay, so here's an image of this. On the top, we have a unit Gaussian, so this would be the reference, and on the bottom we have a more atypical probability distribution that is not a product measure. It's not log concave, but the transport map between those two can pretty easily transform samples from one to samples from another. Okay, now as you probably all know, there are many ways to couple probability densities. Famously, there's optimal transport, which has attracted a lot of attention in the math literature and recently also in machine learning. These maps are called Brenier maps. Another very natural type of coupling between probability densities are triangular maps, and these are the ones that I will focus on. And yet another class of methods are ODE flows. So here one would parameterize velocity fields of ordinary differential equations, and these velocity fields would induce flows which can reshape mass and reshape probability densities. As I said, I'll be focusing on triangular transport maps. These also go by the name of Knote-Rosenblatt maps. Okay, so what makes them triangular, or what lends them the name, is that each component function depends increasingly on many on more variables. So the first component function only depends on the first variable, the second component function depends on two, and so forth. Finally, the last component function will depend on the full x coordinate vector. Okay, and the nice thing is that these KR maps, given a reference and a target and a variable ordering, exist uniquely. So this is a way of pinning down a unique transformation between these two probability measures under very mild assumptions on pi and eta, such as, for instance, them being upper and lower bounded and continuous. And there is a number of other numerical advantages. They're easily invertible, etc. Okay, and as a starting point of analyzing these density estimation and generative modeling methods that are based on transport maps, we considered a very classical non-parametric density estimation setting. In this setting, we're given data from some unknown probability density P0, and we're not assuming anything on the density except that it possesses some kind of smoothness property. But it's not, it doesn't lie in a finite dimensional space. This is really, only smoothness information. So we assume that P0 is in an alpha smooth Hölder class, and we have IID data x1 to xn from P0. And the goal is to infer P0 from x1 to xn. And of course, there have been many approaches for doing this, but the transport-based approach, which is fairly new, would do the following. For instance, it could look like this. Later on, I'll speak about extended versions of this. But here, the objective function for learning the transport map S hat is basically this negative log likelihood of the pullback density of eta under the map S, and we're trying to minimize the negative log density, which is of course equivalent to maximizing the log density. Why I've written it in this way is that this is resembling an empirical version of the Kohlberg-Leiber divergence between the truth and the pullback. And this is a way in which many practitioners have motivated their choice of loss function. So we're actually doing something that somewhat resembles, the Kohlberg-Leiber losses used in practice. And once you've learned such a map S hat by minimizing this objective, you obtain a plug-in estimate P hat just by pulling back the reference. So of course, a key question here is, how do you choose this class curly S of transport maps efficiently? Okay, so I'll note, so one remark to make is that the best possible risk in LP type distances that we can hope for is well known. So this is a minimax lower bound that no estimation procedure can achieve a better estimation rate than n to the minus alpha divided by 2 alpha plus d. So as alpha grows, this rate approaches the parametric estimation rate of n to the minus 1/2. But for any finite alpha, this is slower. And it's well known that an alpha smooth signal can't be estimated at a better rate than this. So in order to achieve this rate, we actually need to study in a detailed way the regularity properties of these Knote-Rosenblatt maps. And it turns out that this class curly S of alpha is the correct class to look at. So these are triangular and bijective maps that are not just C alpha smooth, but that have a certain type of anisotropic smoothness. So if you take the kth component of the map and take the derivative of that component with respect to the last variable, you require that partial derivative also to be C alpha smooth. So in some sense, there's more regularity on the diagonal. And here's a key lemma that that goes into our proofs, which says the following, that fixing a smooth reference, typically, as I said, the reference can be chosen and it can be chosen to be nice. The following two are equivalent for the target to be C alpha smooth and for the unique KR map between the reference and the target to be in this anisotropic S of alpha class, which means that philosophically that this S of alpha class is the correct class to minimize over when we want to model alpha smooth densities. And yes, it turns out that indeed, if you choose a sufficiently large ball in S of alpha to take your minimizer over, you get the following convergence rate. So this is one of our main results in the paper. It says that the expected so mean squared error, if you want, in Hellinger distance between the pullback of the learned transport map and P0 is of this order, n to the minus 2 alpha divided by 2 alpha plus d. And if we recall the minimax rate, the best possible achievable rate from the previous slide, this is exactly matching that minimax rate, where the additional 2 in the exponent comes from squaring the error. So this shows kind of that, at least in terms of rates of convergence, S of alpha is the correct class to look at. The proof idea, due to time, I'll be very brief, uses essentially methods from M estimation, from maximum likelihood estimation that have been developed by Sarah van der Geer and a few others about 10, 20 years ago, and that continue to be used a lot in nonparametric statistics. And so we use the connection of these estimators to maximum likelihood estimation, as well as these anisotropic regularity estimates for triangular maps and metric entropy estimates for the corresponding function spaces that we need. And our paper indeed contains a few more results, because these nonparametric MLEs, while we have shown that they achieve good convergence rates, they might actually be hard to compute. So what people do in practice is they don't want to solve an optimization problem that is kind of constrained to this weird set of functions that have to be bijective and that have to have the right range, etc. They rather come up with clever parametrizations of bijective, like maps with the correct range, etc. So they would kind of come up with a parameter set theta, and this parameter set theta would index a class S theta of maps. So for instance, theta could be neural network parameters, right? In which case that parameter space would be Euclidean. And then they also want to solve unconstrained optimization problems. So that sometimes requires the addition of a penalty term to your objective. So in the end, they would end up with something like this. Sorry, there's a minus missing here, where you're trying to minimize a likelihood term and a penalty term, the sum of the two. Okay, and then our paper has a result which characterizes convergence in terms of general metric entropy properties and bias conditions on the class. And due to time, unfortunately, I can't go into detail. But one takeaway from this is that you can use the general theorem to show that actually wavelet-based parametrizations are able to achieve minimax rates as well. And they're computationally much more convenient. So our paper is currently submitted in review at the Annals of Statistics. One extension we're working on is the case of neural ODEs that I mentioned before. This is work in progress together with Youssef, Robert Wren, and Jakob Zech. And there are other very interesting extensions that we're thinking about, for instance, studying optimal transport maps, and importantly also for the modeling of ray event, the case of actually extending to unbounded space. Thank you very much.